So today we're going to be talking about multiple linear regression and also inferences on a slope for both single and multiple linear regression. And we'll begin there. Okay. So here's a study, and it was an actual study done by these individuals. Okay. They wanted to know why it is that having a larger brain would be more advantageous for an animal, or specifically mammals. Okay. And so they recorded a bunch of data. And the question they ask is, why do some mammals have large brains for their size? Okay. And just to bring up some context, evolutionary biologists are interested in the characteristics that enable a species to withstand the selective mechanism of evolution. An interesting variable is brain size. There are certain drawbacks to brain size, such as larger brains are associated with fewer offspring and lower pregnancies. So we're left to ask, what is the evolutionary advantage for survival of a species? Okay, if you're producing fewer offspring, and why is it that this would be the case? Okay, so here's a little bit of a glimpse of the data set that is involved. Okay, so here's a snippet, and here you have the species, and you have all of them, and this is not all of the species and all of the data. This is just a little peek of it. Okay, so there is more data to this, and here they record the brain size of the species. It's the average brain size. They record the body size, okay, body weight. They record the gestation length, and they record the number of offspring, or the litter size, for the species. Okay. So here's a simple model that we'd revisit from simple linear regression. Okay. And this is the output that I showed you from simple linear regression. And one way to try and predict brain size is by the body weight. Okay. And your regression equation, remember, is formed from the estimate of the coefficients. So there's an intercept of 74.92. That's the base or starting brain size. And for every additional unit of body weight, I believe it's measured in kilograms, but I'd have to double check the data, you would multiply that by 1.3 and add it to the brain size. Okay. And so this is your equation for brain size. Okay. And later in this lecture, I'm going to discuss the meaning of the rest of this output. Okay. So we can use this equation to predict brain sizes. For example, an axis deer has a body weight of 89. So the predicted brain size, we just feed that into the equation, is 192.4. And this is slightly off from the actual value of 219. So we can calculate our residual, and our residual is given by this equation, is 26.6. If we were to do this for every single data point, form the residual for every single data point in the data set, we can form the sum of the squares of the error. This is going to be the residual squared. So SSE, sum of the squares of the error, is just the square of all the residuals. Okay, and that's all that this is. Okay, so another way of thinking of this is the sum of the squares of the residuals. Okay, and the smaller the value of SSE, that means that you have smaller residuals on average. So a smaller value of SSE indicates linear regression fits the data well. Okay. Now, sometimes if you recalculate the slope m, you'll get a different value. And so you can ask the question, is it possible that the slope is 0? That is, you can test the hypothesis that the slope is 0 versus the alternative that the slope is not 0. Is it possible that the reason the slope isn't 0 is due to random differences or random selection in your data? You took a bad sample and it misled you, and that the true value should be 0? Okay, well, we can go ahead and try and test this and test the hypothesis given by this versus this alternative. Okay. Now, one thing to note is that if the slope is 0, then this part of the equation disappears, and you just have that your predicted value is constant. It's that intercept, y equals b. And this intercept b would then become the average. And notice that this equation doesn't depend on x. No matter what you input for x, it doesn't change the average response, your predicted value. Okay, so y doesn't depend on x, and a linear relationship between y and x won't exist under the null hypothesis. If the alternative hypothesis is true, it says that the variable x is important for regression between x and y, and it should be included in its regression equation. Okay, so here's a way to test the hypothesis. We're going to use a t-statistic, and what it's going to be is it's going to be your estimated value of the slope m, and you're going to divide by the standard error. So that is called the standard error, everything that's highlighted. And that is the sum of the squares of the error divided by n minus 2 square rooted, and you divide by your standard deviation of x times the square root of n minus 1. To clarify a few things, n is the sample size, s sub x is the sample standard deviation of x, and m is your estimate of your coefficient of the variable x. This m, that comes from your estimate. So here, our estimate would be this, 1.32. Okay. Now, if we look back at this equation of the output, it provides us the estimate here and here, but it also provides for us the standard error and also the t-statistic or the t-value, okay, here and here. So it allows us to test this hypothesis, but in particular, it gives us the p-value. The p-value is here. That might as well say p-value. Okay, and that's the probability that tests the hypothesis that the slope is 0. Here we can see that the probability is extremely, extremely unlikely to have a slope of 0 under the null hypothesis. It's 2 times 10 to the negative 16th. It's virtually impossible that body size doesn't play a role in predicting brain size. Okay. So one conclusion is that the output provided not only estimates the slope, but it also calculates the t-statistics and provides for you a p-value. Okay, and that body weight definitely should be included in a regression equation between brain size and body weight. Okay. Now, we could have used a different variable to try and predict brain size. Another variable that we had was gestation period. Okay, the longer the gestation, usually the longer the brain size. And here we have that. The gestation length affects brain size, and it's a positive variable. Okay. So for every unit of gestation, it affects the brain size by 3.41 units. And I have to look up what the units were to say exactly how they're measured. But one thing that's of particular importance is that the gestation is definitely important in the regression equation with a p-value of 2 times 10 to the negative 16th. It's impossible, virtually impossible, that this coefficient should be 0. Okay, and it plays a role in predicting brain size. Okay, so looking at this output, I apologize. Brain size, this equation gives us our linear regression equation. For brain size, it says it's 3.41 times the number of gestation days, subtract by 297.75. One thing just to review, some old material, is that this intercept doesn't make sense. Okay. It also doesn't make sense to have no gestation days. So this intercept, which is minus 297, doesn't make sense in this context because gestation days has to be greater than 0. And if it was 0, it's predicting you'd have a negative brain size. It just doesn't make sense. Okay. So that was just a little review. So now that we know gestation plays a role in your regression equation between brain size and gestation, and so does body weight, is it possible to include both variables to try and predict brain size? And the answer is yes. Okay. And the answer is yes, meaning that we could create an equation that involved gestation and and body size to predict brain size. And that's an example of a multiple linear regression equation. Okay. So a multiple linear regression equation has this form. So it has an intercept of b0, but then it has all these variables. It can have as many of them as you want. This equation has k variables. The coefficient of each of the variable is b sub I. Okay. And just as before, we can test the hypothesis that each of these individual variables is important in regression, i.e. that their coefficient is not 0. Okay, and that allows us to judge the importance of each variable for regression. And we can still form predictive values, residuals, and address the regression assumptions, as well as the equation. Okay. Now, one other thing to note is that we can include categorical variables with dummy variables. Let me briefly discuss that. Okay, so here, before I discuss that, here's an equation. Here's the multiple regression equation. And this is the output that you'd see to try and predict brain size based on gestation length and body size. And your equation would be minus 112, that's your base value, plus for every unit of gestation you multiply by 1.44, and for every body weight you multiply by 1.03. Now we can see based on the output here, this is the p-value that tests the hypothesis that each of these estimated values could be 0. Okay. And I apologize. And we see that this p-value is about 1%, so it's statistically significant. It's not likely that the intercept could be 0. It's even less unlikely that gestation could be 0. Okay. And also unlikely that body weight or body size could be 0. So based on the p-value, we can conclude that gestation and body weight play an important role in brain size in grams. And we conclude that for every additional day of gestation, the brain size increases by 1.44 grams, holding all other variables constant. for every additional kilogram of weight, the brain size increases by 1.03 grams, also holding all other variables constant. And one thing is that this model explains about 80% of the data, 80% of the variation in the data. Okay, this is a less conservative estimate, but it's also roughly 80%. Okay, and that's just a review from material we've covered in simple linear regression. You might ask, how is this different than multiple R squared? Well, let me tell you. Okay, the adjusted R squared is an estimation of the proportion of variability that the regression explains in the data, and the R squared explains 80% of the data. That's really good. Okay, and it's a more conservative estimate for the amount of variation that the model explains. And that's to account for the fact that sometimes you can include too many variables in regression. So R squared is a little bit more conservative because when you include more variables, it's possible that you might have chance correlations. Okay, and I won't go into any more detail than that. So adjusted R squared tries to adjust for this and provide a more conservative estimate. Okay. Now our regression equation for brain size, we just read the output. It's minus 112 for the intercept, 1.44 times the gestation days, and 1.03 times the body weight in grams. So for an axis deer, it has a body weight of 89 kilograms, gestation period is 218. So we can predict its brain size. And we just plug in this information, 218, 89 kilograms on average. So it predicts 293.4. We can see that we're a little bit more off, but it just happened to be this one observation. We need a better estimate of all the observations, so don't worry that just this single observation is a little less accurate. Other observations are more accurate, and I know that because the adjusted R squared went up. Okay, so when you do this analysis, it's important to keep in mind that there are assumptions, just like in the simple linear regression. And the assumptions are nearly identical. It's that the residuals are normally distributed. There's constant variance for all the input, across all the input variables. And the data is independent, i.e. it's a random sample of the population. Okay. So it's reasonable to believe that the data is independent. One population's brain size should not affect another mammal's or population's brain size. Okay. Now let's look at the other two assumptions. So independence seems good. Now we need to assess normality and constant variance. So here's the histogram of the residuals. It kind of has a bell shape. It's kind of hard to tell. It kind of resembles a normal distribution, but there do seem to be some outliers. I might say, this histogram, it has a general bell shape. Instead of saying weakly violated, I think that I might say that the histogram indicates a general bell shape. But is hard to assess. And I think that's a more fair assessment. Okay. And there are other statistical methods that help to determine if it is normal. Okay. So I would say further investigation is needed. Some aspects of normality are suspect. Okay. And here's our constant variance. So here's a plot of our predicted of our residuals versus our predicted or fitted values. And it sees that it goes up like right there. Then here, we don't really know what happens. There's not a lot of observations between here and here. It appears that the general trend follows this line, but it's really hard to tell because changing a few of these observations could dramatically affect it. And it's unknown like what's going on right here, if this is truly part of the data. It looks like it is at least weakly violated. If I just looked at this data here, I might be okay with it, but we can't just pick and choose what data to look at. Okay. We would want most of these plots to be right around 0, most of the data points, and to be randomly above or below. Okay. So we're going to proceed with caution and explore alternatives. Okay. Now I'm going to include what's called a dummy variable. Okay, and this is called an indicator variable. It indicates if a single qualitative characteristic is true or false. Okay, so it allows us to have a numerical value for a quantitative response. Okay, so dummy variables allow us to have a categorical input and a quantitative output y. So our next example, we're going to consider sex, and that takes 2 values. It takes 1 if it's male or 0 if female. So true or false, okay, or male or female. And we're going to consider a banking data set. So here, this is a data set we've seen before. It's sex discrimination in employment. And it says data on employees from one job category at a bank was sued for sex discrimination. There are 32 males and 61 females that are hired between 1965 and 1975. For the data set, we'll ignore salary 77 because it should not be used in the regression. That's correlated with Y, with the base salary. Okay. So the idea is that we're going to use any other variable other than sex in salary 77 to determine starting salary. Okay. If they are successful in explaining starting salary, then when you add the variable sex, it should not be significant. That is, its coefficient should be, we should not be able to reject the hypothesis that that coefficient is 0. So it's possible that sex is 0 and that sex doesn't play a role in regression. Okay, so here's a model without sex. I included all the variables. Okay, so I have an intercept. It says seniority helps predict your starting salary, and we can see that that's true according to its p-value. Seniority should not have a value of 0 for its estimate. So meaning it's important for regression, and it predicts the more senior you are, the lower salary you have. Okay. It says that your age, which is also correlated with your seniority, also decreases your salary, but it's possible this variable is 0. Okay. And now education, the more education you have, the higher your salary, and there's a very high p-value for that. So congratulations to everyone in this class. According to this regression model, which is real data, you are increasing your salary. Okay. And also your experience increases your salary by 2.79. And that's statistically significant, meaning that this variable could not be 0. It should definitely be included in the regression. Okay. Now this provides an adjusted R-squared of 28.6%, meaning on the conservative end that this model explains 28% of the data. Okay. Now let's consider this model. Okay. This regression model indicates all the variables are important for regression except for age, and they have been highlighted in red. Okay, you could drop that from the output, but writing down this regression equation says starting salary is modeled by that intercept 5979 plus minus 22.4 times the seniority minus 1.1 times age, 130 times education, and 207 times experience. Okay. Now, I'm going to add the variable sex. Okay. So I'm going to have seniority, age, education, experience, and now I'm going to add sex. And this variable is going to have a value of 1 if the individual is male, and it's going to have a value of 0 if the individual is female. Okay. So here we can see that these variables, seniority, is statistically important for the regression. Age is not. I kept it anyway. Education is important, so I could have dropped age, and I might encourage you to if you want to, but I'm going to let you explain why you include or exclude age. And experience is now not important. Okay. Only education and seniority, so you could drop these from your model if you wanted, and I'd suggest one at a time, because you drop one, it's possible the other one may become statistically important. Okay, and those are details that I'm not going to discuss in full details. And it says when I add sex to this equation, it is statistically significant with a p-value of 5 times 10 to the minus 8th, saying that it's virtually impossible that sex does not play a role in predicting starting salary of an individual. All these other variables are accounted for, so this is a more precise analysis than just a t-test of two populations, because it accounts for their level of seniority, age, education, and experience, where a t-test does not. A t-test would just be comparing starting salary based on male or female. Okay. And one other important metric is that the adjusted R-squared jumped up from 28% to 48%. This model explains 48% of the data, okay, and which is much higher than when I excluded this regression model. And one thing that you should notice is that by including the variable sex, it changed the estimates of all of these. It also made experience now insignificant. Okay, so it can affect both the estimate and if it's important for regression when you add a variable. So please pay attention to that. Okay, so this regression equation, it says that starting salary is given by a base salary of 55.09 minus 22.5 times your seniority minus 0.6 times your age plus 92 times your education plus 0.5 times your experience plus 769 times the value of your sex. Your sex being 1 if you're male and 0 if you're female. So that's emphasized right here. And here's an equivalent formulation. We really have two equations in one. It says that the male starting salary is given by this. I just plug in that they're male, and I keep all of these things the same. But now I plug in a 1 for that value, so I have plus 769. If I'm a female, my equation for starting salary is this. And I plug in a 0 for sex male, so I just leave it off. So if I account for seniority, age, education, and experience, this says that the difference, if all these variables are the same, that the difference in starting salary is $769 for this time period in this industry at this bank. Okay. One thing that I didn't do in this slide is that I could have you predict someone's salary if I gave you their level of seniority, age, education, experience, and sex. So please keep that in mind, because I may ask you that question. Okay. Now, my conclusion here is that based on the p-value that tests if the variable of sex is important for regression, we can reject the hypothesis that the coefficient is 0 at virtually almost any level of significance. Well, and if we want to be more precise, the level of significance would be 5 times 10 to the minus 8th. Okay, which is much less than 0.01%. Okay, and we conclude that the variable sex is important for predicting starting salaries, meaning if you're male or you're female, it makes a difference what your starting salary is. And the proportion of the data that this model explains is about 47%, which is higher than the 26% when we excluded just a single variable. Okay. And finally, the pay difference is $769.9, simply based on that variable. Okay. Well, that's all that we have for a multiple linear regression. Thank you for joining me.